Forgive me if I pronounce your name not correctly. Dr. Tathagata. And he will be talking about the linking flow-induced fiber orientation, fresh UHPC, and hardened UHPC tensile characterizations. And welcome.
Okay, thank you very much. Am I audible in the back? Okay, let me just verify really quick. So good morning, everyone. I am Dr. Tathagata Bhaduri. I am a lecturer at this point in Rensselaer Polytechnic Institute. I worked with Dr. Mohammed Al-Nagar, who is chair of some of the UHPC committees here. So my work is primarily a numerical method which can link the flow-induced fiber orientation in UHPC and how we can use that information which we see in the flow and how we can feed that information in a solid model where we calculate, for example, the tensile strength, flexural strength, and so on. How to do that work. So it's a numerical framework that I will be going through. So I would just start with brief acknowledgement to my colleagues, Dr. Mohammed Al-Nagar, who is now senior research scientist in Oak Ridge National Lab. My previous colleague, Dr. Shadi Goma, he's a postdoc in Northwestern University. And I would also like to thank all the computational resources I have used from Center of Computational Innovation at RPI. So since this session is on UHPC, I'm assuming everyone is already knowledgeable in UHPC. I don't need to spend much time on that. So you all know how is UHPC, how its gradations are, and how the fiber reinforcement helps it to get great amount of tensile strength and post-cracking ductility. That's how it is defined. I mean, it's defined with very high compressive strengths, supposedly more than 120 megapascal, and at least a tensile strength of 5 megapascal, and followed by a sustained tensile cracking strength of 5 megapascal. So one of the challenge you all know already, which is the flow-induced fiber alignments. And the main challenge here is this flow-induced fiber orientation can be dependent on the rheology of the material we are using. There are many variants of UHPC we see every day in a new journal paper in market. There are different variants, different additives which changes and modifies the properties, the rheological properties. But there is also other thing which is called shear history. So if we use a typical type of formwork or mold where the UHPC is flowing, it will also influence definitely the fiber orientation in the domain. So when we are casting, the first goal is we have to identify what is the fiber orientation to understand what is the tensile characteristics of the UHPC we're using. Without that, we cannot define a reasonable certainty of the tensile stress block of UHPC. So my goal is to quantify numerically what is the fiber orientation when we are using a particular device to orient fiber. How can we use that orientation factor and feed that to a solid mechanics model which can give us the data numerically, the tensile strength. So it's completely a numerical framework which will be validated by experimental program. So how this fiber orientation percolates into many other structural designs. I will start with the common failure modes like flexural failure and shear failure. And if I show you the matrix constitutive law in tension, you see that depending on the fiber orientation, you can have super heavy strain hardening, strain softening, and if you have random fiber orientation, it's somewhere in the middle. And if I now combine it with a rebar, with a steel rebar, if the rebar comes there, then the rebar fiber interplay, it typically dominates how the failure will be. So there are already publications which are telling us that the flexural failures in UHPC is very different. You can have a crack localization dominated flexural failure, or you can have a strain hardening dominated flexural failure. If you have more fiber compared to the relative content of steel rebar, you might get a local crack localization, which will cause a more faster failure. It's more like over-reinforcing effect. However, if you have smaller fiber relative to the rebar content, so this thing needs to be defined. So relative reinforcement of fiber is lesser, then you might get a strain hardening type of flexural failure. And to understand this, all these mechanisms, we have in the stress block, either it can be a flexural one or a shear failure one, we have these components coming from fiber, which is itself a function of the matrix constitutive law under tension. So basically the fiber orientation factor embedded in that. So collectively, how can we predict the load deformation behavior as a function of this, fiber orientation factor? Can we do that numerically? So my work is kind of fundamental in nature. It starts with a lot of assumptions because we are just starting this work and we want to build over it. So in that way, it is very rudimentary. The overarching goal of my work is to understand the rebar-fiber interplay and then to inform this kind of model of rebar-fiber interplay with multi-scale modeling and also the flow-induced fiber orientation. So collectively, I want to do this as my long-term goal. I want to make a model which is informed by fiber orientation. I predict the fiber-rebar interplay and how it governs the flexural and shear failure. Then once the model is validated, I can do multi-scaling to predict structural level failure. For example, you want to simulate a failure of girder, a bridge girder. Okay, can we do that? So I use a mesoscale model, which I will be briefly describing in this presentation. So the questions typically I'm trying to ask, okay, if I want to get fiber orientation in UHPC, what is the quantification of that fiber orientation? Okay, if I can quantify that, how does that impact the strength, the tensile strength? If I say, okay, it is oriented, how much oriented is that? What is the degree of orientation? Okay, how to quantify that and how to feed that in a solid mechanics model where fibers are explicitly represented using matrix fiber micromechanics. So that's the main goal of this work, how we can couple the predicted UHPC fiber orientation from the flow model to the solid model. Okay, so I will start with the experimental program that my colleague Shadi Goma did when he was doing his PhD at RPI. So we developed he developed a nozzle like this, with a moving mold to create a fiber orientation. So it's a layered deposition of UHPC to cast a slab sample. And the main mechanism is you create a convergent flow, and after that you add a small another contraction where the exit of the nozzle is the size, the characteristic size is less than the fiber length. So that even if you have some fibers which are not oriented, you force them to be oriented by inducing this dimension. So that was the main hypothesis or rationale behind making this kind of nozzle. So we wanted to see what we get experimentally. So the experimental work was done by casting this slab first. So one test was done on this slab, which was a 3-point bending test on this cast slab. We also did take different, different parts of this slab. For example, along the print path of this slab and also the perpendicular to this print path, we took samples and we did direct tension test on the notched prisms. So that's the experimental part we have. So we want to connect this fresh fluid state UHPC with the hardened solid state. So we want to identify fiber orientation in this experiment. We want to feed that data to the solid mechanics model so that we can predict the capacity of this slab. We can also predict the direct tension behavior just from the fresh state flow. So this is the fresh UHPC model that I used. I used a single phase fluid motion using Navier-Stokes equation. I started with 3 different models. I started with a pure DEM model where both concrete and the fibers are modeled using DEM. So you introduce a lot of particles, which is super expensive computationally. Then I went to CFD DEM, where you use the background fluid using CFD. You introduce fiber with DEM, discrete element model. But when you put that fiber amount like 2%, 3%, it's a very difficult job to perform, even with supercomputers sometimes. So we had to, kind of neglect that part because we had to leave that part. So we came up with some other models motivated by the short fiber reinforcement composites, how they predict the fiber orientation in the extrusion models. So I used that for my study. So I started with a computational fluid domain like this. I simulated the flow in that. This is just a sample picture of the velocity contour and the vorticity throughout the nozzle. Now, once the fresh UHPC model is done, we use this information to predict the fiber orientation. For that, I use Jeffreys' equation. So Jeffreys' equation predicts if you have a Newtonian laminar flow and if you have an ellipsoid in that with the vector defining the ellipsoid. This vector is here, P. So in a Cartesian 3D coordinate, you can show this vector and you can explicitly predict the orientation after a certain length of flow, okay? Later, since explicit modeling of each fiber orientation is very challenging, if you have significant number of fibers in the domain, it becomes very challenging. So there were modifications to Jeffreys' equation by Folger Tucker and then Advani Tucker. They modified this. Instead of tracking each fiber, we come up with the state, the probabilistic state of fiber at different spatial location. So basically what you get is a tensorial form where if all these diagonal entries are representing for each direction x1, x2, x3, what is the orientation probability of that fiber in that direction. If it is perfectly 1, then you will be guessing that, okay, it is perfectly oriented. If it is random, then you have 1 by 3, 1 by 3, 1 by 3 in all 3 different directions. So the total probability added to be 1. So I use this model, and using CFD data, I predict the fiber orientation by solving this differential equation. After solving this differential equation, I can, it's a one-way coupling. We neglect the, we just inform the fiber orientation from the fluid phase. We do not do the back one, coming from fiber due to hydrodynamic interaction because of computational cost. So once this is done, we can feed this data of fiber orientation to a solid mechanics model. We will be using it as a calibration variable so that I can generate random seeds of fiber in a computational domain of solid mechanics. For solid mechanics, I use lattice discrete particle model, which is a mesoscale model which captures concrete mechanics at mesoscale, particularly at core segregate scale. It captures different fracture phenomena like pore collapse and densification, cohesion, and fracture, friction. So this is a lattice-based model. There is a variant of this model which is called lattice discrete particle model F for fiber reinforced concrete, so LDPM-F. It captures all the important micromechanics features which was introduced by Victor Lee long back for ECC type of concrete and which was extended for LDPM-F model. The good feature is in LDPM-F, you can also generate fiber orientation factor. And depending on that, you can simulate different fiber orientation and predict the hardened property of that. So what I do, I predict fiber orientation from my fluid model, coupled with the Jeffreys equation and Folger-Tucker equation. From that information, I calibrate the fiber orientation factor in the solid model. And from that, I can predict the tensile properties and the hardened tensile properties and so on. So collectively, the framework looks like this. I use open source software Phoenix for simulating the fluid flow. From that, I generate the ParaView realization of that to generate the streamlines. From that, I use MATLAB to numerically solve the differential equations for fiber state prediction. Then, using the fiber state prediction in the fresh fluid state, I feed it to the calibration parameter of, in LDPM-F, we call it KF. So that's the calibration parameter that we used, and this is implemented in Morse code. So this is just to show you an example of fiber orientation prediction. So you see, we start with the first case where I have assumed the fiber orientation state is purely random when I'm pouring it. That's why you see a circle. That means that equal probability in both directions in a 2D model. As you go along the flow, you see that it's getting oriented gradually along the flow direction. Similarly, if I start with perfectly oriented state, this is like oriented perfectly along the flow path, you see again it's getting oriented, although it has some changes in the middle. Similarly, if it is perfectly perpendicular to the flow direction, it still orients the fiber at the end. So what we do, we calculate from the streamlines the fiber orientation factor. We feed this data, we generate the fibers in the solid model, we calibrate the fiber orientation factor in the solid model. So this is a 3-point flexural test we did for slabs, and this is the simulation. We see very good agreements with the peak capacity we had for the slab. So this black lines are numerical simulations, and these are the maximum capacities. I can show you a quick example of our result. And on the left, you see the simulated slab with the predicted fiber orientation from the fresh UHPC flow. We also did direct tension tests for perfectly oriented fiber and also perpendicularly oriented fiber. We predict the the fiber-oriented one very well. We didn't do that well in the perpendicular phase because of the limitations we have in the fiber constitutive laws implemented in LDPM-F. So this is another simulation of, so this is the experimental one, and this is the numerically simulated notched direct tension test. So you see how the fibers are bridging the crack, it's perfectly oriented, and this is how it works. So in conclusion, I would like to mention that our model worked reasonably well. I mean, we are still working on it to implement maybe more features because, in a 3D state, you might have fiber-fiber interactions. You might have clogging at the exit of nozzle. So there are many different factors, okay? Sometimes, when you're depositing it, you might have phase changes. You might have thermal changes, heat transfer. So it becomes very complex model. So this is very much fundamental model with a focus to only identify the fiber orientation. And it does it reasonably well. And I showed you that the results agreed very well with the experimental counterpart. So, so this is kind of the future work that we are proposing. And we see that one-way coupling in this work worked reasonably well. And we want to see and validate more different numerical models like this, numerical experiments like this to make confidence on this particular development.